Previously on the finite element videos, we stated the problem that we'll be using for our two-dimensional development. We will use the same problem for both the triangles and the quadrilaterals. The problem is basically that we are releasing a contaminant within a channel flow, and we want to see how it disperses over time. So in the previous video, we had the first three steps of the formulation. So we started by stating the governing equation for the physics. That was our partial differential equation and our starting point. So the first three steps, we approximated C by C hat, we stated the residual, we stated the weighted residual. Now it's time to move on to integration by parts in two dimensions. We developed the governing equation, and then we took the first three steps of the finite element formulation. Let's just write the governing equation again, just so that we have it to work with. It was the partial of C with respect to time, plus the convection term was balanced by, make this d sub d because that's the material property, it's balanced by the diffusion term and the source term. So let's look at some of these terms first before we actually move forward with our analysis. The first term I want to look at is this term right here, the convective term. So let's look at our convective term. If we expand that, what we have is Vx dc dx plus Vy dc dy. Now, we know that Vy is equal to 0. It was one of our assumptions that we have plane Poiseuille flow. So this term actually goes away. Okay, let's look at this term here, the diffusion term. So for our diffusion term, we said that d sub d, we said that we have constant material properties. So that means that for this term here, we will get d sub d del dot del c. So now, if we rewrite our equation, what we have for our governing equation is dc dt plus dx dc dx is equal to d sub d del dot del c plus f, where f is our source or sink. So now our weighted residual equation will look like 0 to h, 0 to l, w, x comma y, dc hat dt, dx dy, minus the integral 0 to h. I'm rearranging them a little bit, bear with me, w sub x y, d sub d, del dot del c hat dx dy, plus the integral 0 to h, 0 to l, w x comma y, v sub x dc hat dx dx dy, minus the integral of 0 to h, 0 to l, f w of x comma y dx dy. Okay, now we're ready to consider integration by parts on our second order term, which is our diffusion term. And we'll start that on the next slide. Integration by part. Now, what we want to mention is that we're now going to look at the general form. So I'll go back and just remind you that in 1D we had the integral of u dv, and we found u, we found v, and we got minus v du plus the boundary term.
So now the general form is Green's theorem. And that general form is that you have an integral over a volume. It's a volume integral now. And you have u dot dv, d volume, is equal to minus the integral over volume of v dot du, d volume, plus the integral over the surface of u v dot n, where n is a vector, times d surface. So a couple of things to note. One, we have area, not volume, right? We have an integral, two integrals, dx dy, which we can write as integral over the area times d area. So in that case, it becomes for us integral over the area u dot dv, d area, equal to minus v dot du, d area, and this is also over the area, plus the surface now becomes an edge. So this is I'll even just refer to it as an edge, u v dot n. And now we need to talk a little bit about this n, and this is, I guess it's the edge. So the n here, this n is a unit vector. It's the normal, basically. So it's the outward normal. So you have to be careful because it's a unit vector, but it has a sign. And that will depend on which way your coordinate system is. You need to remember to account for the sign. Okay, so how are we going to go about using this? Let's apply Green's function to our problem. So just remember, we're starting now with minus, and then I'll write the equation. And I think what I'll do is I will do it as the area. So we have the term that we're looking at is w of x comma y, d sub d, del dot del c hat, d area. So I've shifted now from using dx dy to d area. Okay, this is our second order term. So I'm going to write in green what our integral was. So it was over the area. And I'm writing it because I want to point out the sign. Okay, I will call out here again the sign. Note those two signs, because what we're going to get when we look at applying Green's theorem, and when we do that, we are going to have the integral of a d sub d del w dot del c hat dA minus, I think what I'll do is do that here. I'm going to do the minus here and the plus here because these signs have changed compared to what we're used to because we have the minus in front of the d. So minus the integral over the edge of d sub d, which is the diffusion of w del c hat dot n d edge. Okay. The next thing I want to do is I want to look at this term. This term should be familiar to you because this term was part of the very first homework. Remember that w is a function of x and y, and c is also a function of x and y. This term becomes d sub d integral over a of dw dx times x hat, which is the unit vector in the x direction, plus dw dy, y hat, the unit vector in the y dimension, dotted with dc hat dx, x hat, plus dc hat dy, y hat, dA. So basically now, do the dot product, and we will get an integration by parts result that looks like integral over a, d sub d, our diffusion, times dw dx, dc hat dx, plus dw dy, dc hat dy, d area, minus the integral over the edge, across the edge, w del c hat dot n d edge, and there should be a d sub d. This is our result from the integration by parts. Our next step is to state the continuous formulation. And if we look at our continuous formulation, adding in our integration by parts, we now have the integral over the area of w x comma y dc hat dt dA plus d sub d integral over the area dw dx dc hat dx plus dw dy dc hat dy d area minus d sub d integral over the edge of w del c hat dot n d edge plus integral over the area of vx dc hat dx w of x comma y d area minus integral over the area s times w of x comma y d area would be equal to 0. That's our complete continuous formulation. And I'm going to put the tilde because we know that it's going to approach the residual and we're going to drive the residual to 0. Okay, so if we have that, the next step is to create the discrete formulation.